In this video, we're going to talk about transformations of functions. So there's three main types of transformations that we're going to talk about for graphs of functions. We're going to talk about shifting them left and right. We're going to talk about stretching them or smashing them, stretching or compressing, or we're going to talk about reflecting them. All right, so first, let's talk about shifting horizontally. We've actually seen a little bit of these transformations when we talked about finding a vertex for a parabola and whether or not that parabola opened up or down. We saw the shifting of the vertex, and we also saw the stretching by that coefficient of a in front, and then we saw the reflection with the negative in front of it. So we've already seen a little bit of this, but let's just see if we can make it a little bit more formal and show what happens for any type of function rather than just quadratics. So for this one with a specific example, let's look at the graph of f of x equals x cubed. And let's see what happens when we add and subtract numbers on the inside of that function. So what I mean is, if we replace the x with an x minus c on the inside, let's see what happens as we change those values of c. So we've moved over here to our graphing calculator. Here is the graph of f of x equals x cubed. And what we're going to do is just, let's say we want to make c positive. Just start pulling. I'm going to pull this slider over to the right, make c more and more positive. Notice that the graph is being shifted horizontally. Notice here, for example, when c is 1, we've taken the point that was at the origin, and it's now at the point 1, 0. If I move over to c equal to 2, I now have the point that was the origin 2 units to the right. And so on. If I scroll over a little bit more, let's say I go all the way to 5, I see that I've taken the original f of x equals x cubed and moved it right 5 units. If we move that c value to the other side, let's say we go -1 here, I've moved it 1 unit to the left. And notice if we put -1 in for c here, we would have x plus 1 cubed. Again, move it over to -2, we've gone left 2 units. Or if I scroll over really far, maybe I do put in -8, I get, this has been shifted to the left 8 units. Now that we've seen what a number does on the inside of a function if we add or subtract it, let's see what happens when we add or subtract a number on the outside of the function. So in this one, let's look at a specific example. Let's start with the graph of f of x equals absolute value of x, and let's see what happens when we add or subtract numbers on the outside of that absolute value. So for example, if we have an absolute value of x plus d for various values of d, let's see what happens. Again, switching over to the graphing calculator. Here's my graph of absolute value of x. I'm going to use the slider to put in different values for d. Let's do to the right again first to the positive side. Notice that here, if I shift it all the way over to 1, this point that was at the origin, we've moved it up to the point 0, 1. If I move my d up to 2, I've taken that point that was at the origin and moved it up to 0, 2. And again, the farther I move to the right, the farther this goes up. So say I put 6 in for d, we've now gone 6 units up. All right, so what happens if we go to the left, putting in negative numbers? Let's say we go to -1. If we put in -1 for d, notice that this point that was at the origin is now down at the point 0, -1. Put in -2 for d, we've gone down 2 units. Again, think about if we put even bigger numbers in, maybe we put in -9 for d, we've moved all the way down here 9 units. So let's see if we can piece all of this together. So if we have an arbitrary function, f of x, and we want to graph y equals f of x minus c, meaning we've replaced every instance with x with an x minus c, or said another way, we've taken a c and subtracted it on the inside of the function. We shift right if that c is positive, really means we're subtracting a positive number. We go left, absolute value of c units, if c is negative, meaning we have an x plus some number. If we've added instead on the outside, we go up if the d is positive, we go down if the d is negative, and we go down by an absolute value of d units. So Adding and subtracting a number on the inside of the function moves it left and right. Adding and subtracting a number on the outside of the function moves it up and down. Let's move to the next case where we do a stretch or a compress horizontally. Just like before, we're going to look at a specific example. So let's look at the function f of x equals square root of x. And let's see what happens if we multiply and divide the x by some number. So let's see what happens. Alright, so we're starting with the graph of y equals square root of x. We're going to multiply by positive values of b. We'll handle negative values here in a little bit, but let's just do positive values of b. Let's see what happens if we make that b bigger than 1. If we make that b bigger than 1, say we make it 2, whoops. We make it 2, notice that the original graph here is in red. We've now got this blue graph that is, well, it looks taller. What's happening is we're compressing it horizontally. So for example, if I move it to 3, it's getting smashed more towards the y-axis. The bigger I make the b, the more and more it gets smashed towards the y-axis. So in this case, we get a horizontal compression. All right, well, what happens if I take my b and make it less than 1? Well, notice here, we're getting a horizontal stretch. It's making it pulled more in the positive x direction. So that's what we mean by a horizontal stretch. We're taking these points and we're pulling them this way. Okay. So the smaller the b gets, the more and more stretched out it gets. All right, so we've handled some horizontal stretching and compressing. Let's look at some vertical stretching and compressing. So let's start with the graph of f of x equals 1 over x, and let's see what happens when we multiply and divide by numbers on the outside of the reciprocal. Inside of the reciprocal would be on the bottom. So we're taking numbers and multiplying it on the top. So we're going to look at a over x for various positive values of a. Okay, so here's our original graph of f of x equals 1 over x. Let's start pulling our a values to be more and more, be bigger and bigger than 1. More and more, getting larger and larger, I should say. All right, so remember when we put larger and larger values on the inside of the function, we started smashing towards the y-axis, right? It was compressing it horizontally. But notice here, if I take it and multiply everything by 2, the red's the original, we're getting bigger. It's multiplying all those y-coordinates by 2. Here we would be multiplying all the y-coordinates by 3. Here we would be multiplying all the y-coordinates by 5. And so on down the line. So notice that the larger we make the a value, the bigger that we multiply by, the farther away from the axis it gets. What happens if we go less than 1? Well, if it's stretching it, if it's bigger than 1, you can probably guess that it's going to compress it if it's less than 1. Which is exactly what happens. So what conclusions can we draw? So if we want to sketch the graph of y equals f of bx, meaning that we've replaced all the x's with b times x, or the b has been multiplied on the inside, we get compressed horizontally by the reciprocal. If b is greater than 1, we get stretched horizontally by the reciprocal if b is between 0 and 1. If we want to graph a constant times f of x, or multiplying on the outside by a, this was going to stretch it vertically by a units. If a is greater than if a is greater than 1, this should be a 1, not a 0. This should say if a is greater than 1. We compress vertically if a is between 0 and 1. So it should say 0 is less than a is less than 1. I apologize for the typo. Okay, so again, stretch vertically if it's bigger than 1. Compress vertically if it's between 0 and 1. Okay, so those are incorrect. All right, so now let's do the last transformation that we're going to talk about, and those are reflections. So much like what we did with the other ones, let's look at a specific example and see what happens. We're going to take the x and make it a negative x. We're going to replace the x with minus x and see what happens. There's not much sliding to do here in this case because we've literally just replaced x with minus x. The original graph here is in red. Here's your f of x equals root x. When we put a minus in the inside, it's flipped it across the y-axis. Let's see what happens when we multiply by a -1 on the outside of the function. So here let's start with the function f of x equals absolute value of x, and see what happens when we do the graph of f of x equals negative absolute value of x. So the original graph here for absolute value of x is in red. Here's the graph of negative absolute value of x that's been reflected across the x-axis. So what can we conclude from this? Well, if we replace the x with a negative x on the inside, or again think about multiplying on the inside of the function by a -1, we get a reflection across the y-axis. If we multiply on the outside of the function by a -1, we get a reflection across the x-axis. So what we'll concentrate on in further subsequent example videos and in class will be putting all of these together to get graphs of new functions from old ones.